expression for torque in terms of moment of inertia. Expression of torque or for torque, you consider a rigid body of any shape, and this rigid body is rotate about axis of rotation with constant angular acceleration alpha. Also, suppose this is the center of that axis of rotation, and this rigid body made up of n number of particles. This rigid body consists of n number of particles, and each particle having mass m1, m2 up to so on mn. The mass of particle is m1, m2 up to so on mn, and this particle situated at distance r1, r2 and rn from the center of that axis of rotation. These masses are situated at distance r1, r2 up to so on rn. This rigid body is rotate with constant angular acceleration alpha, but having linear acceleration is not same or constant. That is, the linear acceleration of this rigid body is not same or is different. Then we find out the linear acceleration of that rigid body. If this rigid body rotates about its axis of rotation, then these small particles having mass m1, m2 up to so on mn, this small particle is also rotate in same axis of rotation with same angular acceleration alpha. But each and every small particles having mass m1, m2, m3 up to so on having linear acceleration is different. Now we find out the linear acceleration of first particle. Linear acceleration of first particle having mass m1, a1 is equal to r1 alpha. Similarly, for second particle, a2 is equal to r2 alpha, and finally for last particle, an is equal to rn alpha. These are the linear acceleration of these small particles having mass m1, m2 up to so on mn. Therefore, also we calculate the force is exerted on these particles. Let the force F1 is acting on particle M1, force F2 is acting on particle M2, and force Fn acting on particle whose mass Mn. Now we find out the force on first particle. F1. The force on first particle is say F1 is equal to M1 A1. But we use value of A1, therefore M1 R1. Similarly, for second particle, the value of F2 is M2 A2 and M2 R2 alpha. This is the force. And finally, the last particle, the force Fn is equal to Mn An is equal to Mn Rn alpha. This is the force on each particle. Now we find out the torque on each particle. For first particle, the torque is τ1 is equal to F1 into R1. This is the definition of torque. For first particle with mass M1, the torque is τ1 is equal to F1 into R1. Therefore, τ1 is equal to values of F1 is M1 R1 square into. For second particle, τ2 is equal to F2 R2 using value of F2 M2 R2 square alpha. And for last particle, τn is equal to Fn Rn. Therefore, τn is equal to Mn Rn square alpha. This is the torque of first particle whose mass M1, second particle whose mass M2 and last particle whose mass Mn. Now we find out the total torque acting on that rigid body or whole rigid body. The total torque τ is equal to τ1 plus τ2 plus up to so on plus τn. Therefore, τ is equal to values of τ1 M1 R1 square alpha plus M2 R2 square alpha plus up to so on plus Mn Rn square alpha. Therefore, τ is equal to alpha is constant into bracket M1 R1 square plus M2 R2 square plus up to so on Mn Rn square. But this bracket is nothing but a definition of moment of inertia. Therefore, τ is equal to alpha into R, where R is the moment of inertia. Therefore, finally, the torque τ is equal to I into alpha. This is the expression of torque in terms of moment of inertia when this rigid body rotate about its axis of rotation and attain the constant angular acceleration alpha. Τ is equal to I alpha, where τ is torque acting on that total body, I means moment of inertia of that total body, alpha means angular acceleration, and this equation is analogous to F is equal to M into A. F is equal to MA. This equation is in linear motion and this equation is in rotational motion. Hence, the torque is analogous to force, moment of inertia is analogous to mass, and angular acceleration is analogous to angular linear acceleration. This is the torque on that body. Now we discuss another topic in same topic, same chapter, that is rotational dynamics. The topic is law of conservation momentum. The law of conservation of angular momentum statement. If no external torque acting on rigid body or given rigid body, if no external torque acting on rigid body, then the total angular momentum of the same rigid body is equal to constant or conserved. This is the statement of law of conservation of angular momentum. If the no external torque acting on any rigid body, then the total angular momentum of that or same body is equal to constant or conserved. We know that the angular momentum is given as L, or L is equal to constant. This is called the law of conservation of angular momentum. Now we discuss about the proof of that statement. Proof. According to definition of angular momentum, L bar is equal to R bar cross P bar, where P bar means linear momentum, R means moment R, and L means angular momentum. Now we differentiate or take the derivative of both sides, we get dl upon dt is equal to R bar into dp bar upon dt plus P bar into dr bar upon dt. But dp bar upon dt is nothing but force and dr bar upon dt is nothing but velocity. Distance upon time, or this is dp bar upon dt means force. Therefore, dl bar upon dt is equal to R bar cross F bar plus P bar cross P bar. But P bar is equal to M into P bar. Therefore, dl bar upon dt is equal to R bar cross F bar plus M P bar cross P bar. But P bar cross P bar is equal to 0. Therefore, dl upon dt is equal to R bar cross F bar. The whole term is 0. But this R bar cross F bar is nothing but toe bar, definition of torque. And if toe bar is equal to 0 according to statement, if no external torque acting on that rigid body, hence toe is equal to 0, dl bar upon dt is equal to 0. Hence, or this gives L is equal to constant. If the dl bar upon dt, the derivative is 0, hence L is equal to constant, and the L is nothing but angular momentum. This is the law of conservation of angular moment.